So that last time we were talking about the quantum product. So I've written this here, and it's just what's called the small version of quantum cohomology. You can also deform by what's called the bulk deformation, and then get a whole family of products. But this would be called the quantum product at zero. So if I have two classes Vi and Cj, then I take their product by summing overall, summing over a basis, and also summing over all possible curve classes. And then I count the maps of the particular class beta, which map 0 to the first cycle, 1 to the second cycle, and infinity to the dual of Ck. And when I put these in general position, I get a well-defined count, which by definition is 0 if the number is infinite. It could be you get infinitely switch mapped. You need to declare the count is 0 in that case. And a special case would be when beta is equal to 0. Then you're just taking the classical intersection product, and for example, if I intersect two cycles, if they're not necessarily complex, I have to look at the sign at each intersection point to get the intersection number. So a typical example would be if I take, for example, M to be the complex projective space, and I take the product of 2 points. Well, classically, the product of 2 points is 0 if n is bigger than or equal to 2, because in general position, 2 points just don't intersect. So the cohomology class will also be 0. But in quantum cohomology, there's a line. Regardless of where you put the 2 points, there's a line through them. And so there's a map of degree 1, and that's going to intersect a hyperplane at some point. So if you dualize the hyperplane, you get a line. So the typical example of a quantum product would look like this. And this also works equivariantly. And I won't really need the equivariant extension for the examples that I was going to talk about in the course. I mean, either I'm going to be using equivariant cohomology or quantum cohomology, but not equivariant quantum cohomology. But let me just make, in response to, there was a question from the audience last time. How do you define it equivariantly if you need the basis and the dual basis? So you need the equivariant Poincare pairing. So the equivariant Poincare pairing, you take a form on M and another form on M. And so let's call the forms gamma 1 and gamma 2. And I take the integral over M of gamma 1 wedge gamma 2. And because this is a equivariant forms, they're maps from the Lie algebra to forms. Here I don't just get a real number, I get one of these invariant polynomials. And this pairing is not in general non-degenerate. But if in the case that M is compact with Hamiltonian action, so that means that there's some moment map Kirwan proves in her thesis that the equivariant cohomology of M is it is just as a vector space. So this is additively the cohomology tensor with the space of polynomials. So in particular, any ordinary cohomology class in HM has an equivariant extension. And if you think about what this means a little bit, you realize that this implies non-degeneracy of the equivariant Poincare pairing for these spaces. So really just the same definition that we had before still works to define the quantum equivariant cohomology. You can in fact just take the same basis that you had before of cycles and just take equivariant extensions. Okay. Were there any other questions about that kind of thing? This technique of proof was really the same technique that she used to prove the surjectivity result, which was that there's a spectral sequence, and then you compute the Poincare polynomial. And let me just make a side remark. Since we're talking about Kirwan's work again, that Kirwan's surjectivity also holds equivariantly. So in particular, if I take a vector space Cn, and this has an action of the scalars acting on each factor, then the equivariant cohomology of M surjects onto the equivariant cohomology for the reduced space, where T red is this residual torus action. U1 to the n mod the G that was acting. And so we get a presentation of the equivariant cohomology of the toric manifolds from this Kirwan map. And so it's natural to ask, what are the relations? And the relations in the equivariant case are actually easier than the relations in the non-equivariant case. The relations are just the nonlinear ones. I mean, you sort of know there have to be fewer relations, right? Because the equivariant cohomology is bigger than the ordinary cohomology. But you're getting a surjection from essentially the same ring, polynomial ring that you had before, the ring generated by the divisor classes. So it's just the nonlinear one. Let me just give an example of that. So suppose M is C2. So M red is CP1, just the two sphere. And then the polytope here is the interval from 0 to 1. So you have two facets here. You have the point over 0 and point over 1. And so HS1 of CP1 is generated by there's the point at 0, which is the inverse image of let's just call it B, for B either 0 or 1. But now point times 0 times point times 0, there's no longer a relation. Okay, like in classical cohomology, if I would take the square, sorry, it's not the quantum product, it's the ordinary cup product. This is not a relation, so that's not 0, but a point times 0 top point times 1. So the two different points, that is 0 in equivariant cohomology. And that's the only relation. So another way to write this is HS1 CP1 is generated by two generators, X and Y, with a single relation XY equals 0. X would be the point at 0, and Y would be the point at 1. So that's in contrast with ordinary cohomology, would be CX, X squared equals 0. Any questions? Any other questions from last time? Okay, so we started talking about vortices. So we said that now suppose that C is a complex curve, and P over C is a G bundle. And then I can look at the space of gauged holomorphic maps. With bundle P, so that's the space of pairs AU. So that A is a connection on P, and U is a map from C to the associated G bundle. And the underlying, the subscript P here means that the underlying bundle is P. And this has a symplectic form. Okay, well, okay, what kind of space is this? So in good cases, this can be made into a Banach manifold. And in these good cases, there's a symplectic form where I think of a tangent vector as an infinitesimal deformation of the map and the connection. And so I put these in together. Sort of the standard way is to take, there's some sort of way of combining one infinitesimal deformations of the connection to a two form. And then there's a way of plugging in the infinitesimal deformations of the map into omega. This gives a zero form C, and then I have to pick a volume form. So the whole theory, if you want the moment map, it depends on this choice of a volume form of C. And then the space of vortices is the is the reduced space. So it's the symplectic quotient. for the action of the group of gauge transformations. And the moment map is this combination of the curvature and the moment map for the action of G on M. And so I mod out here by G of P. So P of phi, this is the map from P of M to P of G dual, which is isomorphic to P of V, induced by phi. And so that then we can try and get vortex invariance by, so similar to the Gromov-Wood invariance used in the definition of quantum cohomology. And for this, we need evaluation maps. So there's a framed version of this. Where you choose some points in the curve, and then you have trivializations of the fibers at those points. And so then there's an evaluation map to M to the D. On the other hand, there's a projection to the unframed version where you just forget the framings. Okay, so then by pullback, we get maps from the equivariant cohomology to the equivariant cohomology of the framed version. And this is equal to the cohomology of the unframed version. Because again, this action of G to the D is the action that changes the framing at those markers. And so then in good cases, you can, integrate.
There is a question in the chat.
Is the evaluation method? Well, the trivialization is now part of the data. So the bracket here, so that this superscript framing is meant to indicate that the trivializations here can vary. And any two trivializations will be related by some action of G. So once you have the trivial, oops, what happened to my next? Yeah, once you have the trivialization, then you get this map from vortices to the manifold. And then here, this is the map which forgets the trivialization. So when you put these together, you get map from HG of M to H of a vortex space. And then in good cases, you can integrate and get some map to Q. And so then this collection of maps, this is what we would call the vortex invariant. So somehow the fact that the map is not independent of the choice of trivialization, that's why you have to take vortex invariance looping maps from the equivariant homology of them. And yeah, any other questions? Okay, so there's a interesting question which was raised by there's not just one trivialization, right? There are many trivializations, and so all of those trivializations are part of this frame moduli space. So you're considering all trivializations at once. There's never any point at which you only have one trivialization. Does it make sense? So there's a very interesting large area limit, which was studied by Guile and Solomon, and then Ziltner. And so the question is, can we recover the curve counts in the MRED from the vortex invariance? Okay, so what you can do is you can take a limit. Let's take a sequence going to infinity in OR. And suppose I have a sequence of vortices satisfying the vortex equation, but with the volume form changed by this parameter. And we saw before that, if you have a holomorphic map in MRED, you can think of it as a vortex with this second term, just infinite. So you hope that you can sort of go the other direction, vortices to maps in MRED. There's a problem. So the good case is when the supremums of these maps are bounded, and then you do get convergence to a holomorphic map in MRED. But in general, there's bubbling of what are called affine vortices. And so the affine vortex is a pair AU, where A is a one form on R2 with values in G, and U is a map from R2 to M, satisfying well, the same equation as before, but then when you do this second equation, the volume form just becomes this infinite volume form on R2 dx dy, which is invariant under translation. So the picture is that a vortex sequence AU, UNU can converge to some configuration where you have not only map to the reduced space, but also you have some affine vortices. Maybe it's just better if I, instead of trying to write on this, because the print size is not so great. Well, let me also change the color. So the pink things will be some affine vortices. And then in addition to that, in the case that the original manifold, I'm really just thinking mostly in the case that the original manifold was a vector space, but in general, you can also get some additional bubbles, which are holomorphic maps to M. And this picture also uses some results of odd. On the removal of singularities. Okay, so what was the hope of Gaio and Solomon?
Chris?
Yeah,
Can I ask you a question about that last picture?
Sure.
Can you show it again? So the picture is supposed to be that I'm getting a curve inside the reduced manifold, possibly some affine vortices bubbling off, but then you're saying that those other holomorphic maps don't even have to lie in like the 0 level of the moment map?
Right, exactly. Yeah.
And the red ones can bubble off of anything or only the affine vortices?
So it's a little, you can always stick in these so-called ghost bubbles, so that suppose at first it looked like the red thing bubbled off the blue thing.
Yeah.
You could always stick in a constant vortex in between.
I see.
So that they're always separated by some pink bubble.
Okay, great.
It's a little bit like in Gromov-Witten theory, when you have like 4 bubbles and they all seem to meet at the same point, and you just stick in a ghost bubble so that they the nodes don't coincide with each other.
I see. Thank you.
Yeah, and the way to think about this is as sort of, if I go back to the previous slide, so these bubblings are happening when this condition is not satisfied. But if it's not satisfied, you have to compare the rate of blowup with the rate of the constants rho sub nu. So if this blowup of the first derivative happens much faster than the blowup of the rows, that's the case when you're going to get a red bubble. If it happens at exactly the same rate as the blowup of the rows, then you're going to get a pink bubble. And if it happens slower than the blowup of the rows, then you're just going to end up with a holomorphic map to M red. So there can also be some other, I mean, this map to U red, it doesn't have to be irreducible. I mean, it could also have other bubbles in between here. I'm just sort of agglomerating those into one big blob to not confuse the picture. Any other questions? So the hope of the Gaio-Solomon hoped that counting the vortices would define a map from the quantum cohomology to the quantum cohomology of n red. Well, how would that map work? Well, you know, you have now evaluation maps. So now let's let the G framed with one marking be the space of framed affine vortices. With a single marking. That's finite. Okay, well, evaluation at that marking gives me a point in M. But on the other hand, I have this other evaluation map, which is what happens when I go to infinity. And when you think about what this equation does, I mean, it's the volume form is going to infinity as you move to infinity on R2. And the equation forces the moment map to go to 0 in this limit. So in the limit, you actually get an evaluation map to n red. Okay, so then if I look and start with the equivariant cohomology of M, I can then pull back to the equivariant cohomology of the moduli space of frame vortices. This is the same thing as the ordinary cohomology of the moduli space of the unframed vortices. And then I can hope that I can integrate and get something in the ordinary cohomology of M. But when I sum over all possible, these are non-compact moduli spaces here. So in order to get these things to be convergent, you need to throw in a formal parameter. So I can really only expect this map once I go to Q8. So the hope is that this would be a quantum analog of Kirwan's map. And in particular, you expect this map, which I'll denote by QK, to be a star homomorphism. So what's the basic idea? Well, if I'm given classes gamma 1 and gamma 2 in the quantum cohomology of in red, then I want to compare QK of gamma 1 star gamma 2 to QK of gamma 1 star QK gamma 2. And there are pictures that go along with these two expressions. So if I take the product first in gamma 1 and gamma 2 in M, then I'm looking at pictures like this. And then QK means I have a vortex. So then I'm counting vortices and I'm seeing what comes out here. And then in this other picture, I first would apply QK to gamma 1 and gamma 2. And then I would take their their product in M and see what comes out here. And there's a natural cobordism between these two moduli spaces of configurations. So the cobordism is a cobordism when I just have vortices and I have two markings and an output. And this can degenerate to either of these pictures as either, as these 2 points come together, then you get the picture to the left, or as the 2 points move apart, you get the picture to the right. But there are various problems with this. One problem is that in general, there's additional buckle. So you don't quite get the relation that they hoped, but you get something similar, which involves this bulk deformed quantum product that we talked about a little bit in response to a question mark. So now, if you really want to compute these, what you really need to do are find some holomorphic descriptions. Well, now we have two moduli spaces. We have the moduli space vortices in M, and we have the moduli with a compact curve. And then we also have this moduli space of vortices where the domain is this R2. And so the description of the first one is due to Mundet. And it says that VGCM is the space of pairs where P is a holomorphic GC bundle and U is a holomorphic section satisfying some semi-stability condition. And then you mod out by complex gauge transformations of the. And then obviously you have to take a union over isoclasses of P. And Sushmita and I had a simpler description of the moduli space of affine vortices on our paper. Guangbo also had a similar description in some other cases. So it says, if you want to know what the affine vortices are, well, you have pairs P comma U, where P is a bundle on P1, and U is a section of the associated bundle, such that U infinity is semi-stable. And then there's some notion of equivalence. Which it's a little bit different than the notion of equivalence for these other vortices. There's some automorphisms of the domain that are allowed, which correspond to translations in R2. Okay, well, what's an example? let's take M to be Cn. And so then we know that Hg of M is just a polynomial ring in a single generator that I call T. And let's look at the moduli space of vortices from R2 to M of class degree corresponding to 1. Okay, so then I'm just looking at maps from R2 to Cn, they're holomorphic. So these are polynomials. That are just of degree 1. So A0 plus, I started with A1 plus B1z up to AN plus BNZ. And the condition that at infinity you get something semi-stable translates into the condition that the leading order term is not equal to 0. And let's take the marking at d equals 0. So here you sort of see what the two evaluation maps are. So you have one evaluation map which maps to A1 up to AN. And then you have another evaluation map at infinity, which maps to B1 up to Bn. And of course, that evaluation map, the first evaluation map is only once you have a framing. It's not really well defined until. Okay, well, remember what relation we're expecting to get. So the quantum cohomology of Tn minus 1, remember the relation was there's a T variable and there's a Q variable, and the relation is that Tn equals Q. So this corresponds to the fact that, again, if you just take a point and a hyperplane, then once you fix another point, you get invariant 1. And so you dualize that point, and this dualizes to Pn minus 1. So this would be Tn minus 1, and this would be T. So you're taking T times Tn minus 1, and you're getting 1 times Q. Okay, so how do you see that from this quantum Kirwan point of view? So we expect Qk Tn to equal Q. Well, what is it? Well, I have to pull back under the evaluation map T to the n, and then I have to push forward under the evaluation map at infinity, and then there's going to be a Q if I only integrate over degree 1 vortices. And there are going to be some other terms, but you can check that the other terms from other degrees don't contribute. Okay, well, how should I think of this T to the n? Well, T we said is the first Chern class of this bundle with weight 1. I mean, it's a trivial bundle, but its equivariant structure is not trivial. And so when you pull this back, this is the product of those Chern classes. This is the Euler class of the bundle on Cn with fiber Cn over the moduli space of vortices. And another way of writing an Euler class is to say that I want to take a section of that bundle and take the dual class to the zero locus of that section. So I have a choice here. And the choice here is to take U and
What's the bundle here? Can you remind me?
so it's just the trivial bundle, but it's pulled back to the space of vortices. But I identify it with the bundle whose coordinates are A1 up to AN. That's one way of thinking about it. So anytime I have a bundle on M, I can pull back to a bundle on the space of vortices, right? So I just take the trivial bundle on M with weight 1, but with n copies of it, and pull it back. And then I can identify that with the bundle on the space of vortices, which corresponds to the coordinates A1 up to AN.
Okay.
So I take this to be my section. This is giving me an n-tuple of complex numbers. And remember, my bundle is just the trivial bundle, right? So I just have to take a section of a trivial bundle means I take n holomorphic functions. So these are my n holomorphic functions. I just have to check that they behave the right way equivariantly, because I'm doing everything equivariantly for this action of u1 to the n. Okay, so then S inverse of 0 is just the space of now it's vortices which have no a's in them. So u of z is equal to v1v up to vnv. And I want to push that forward under the evaluation of an infinity. It is just of infinity of this space of vortices. v1z up to vnz. And when I evaluate at infinity, I do just get CPN minus 1. Okay, so the conclusion is that qk of t to the n is q times ev infinity star of ev star of t to the n. I thought of that as an Euler class. I took a section which just gave me vortices with only b's in them, and then I push that forward, and I get just q times the unit, because this is the unit in the homology of CPN minus 1. So the kernel of the quantum Kirwan map is the ideal generated by t to the n minus q, and that says the quantum homology Cpn minus 1 is this ring generated by these two variables with a single relation. Now, in this case, it's a little bit silly to do it this way because you already knew what the relation was from just looking at the fact that any 2 points are generated are joined by a unique line. But the point is that this generalizes to arbitrary toric manifolds. And in the case of arbitrary toric manifolds, the kernel of QK is what are called the Bati-Rev relations. So for each element D, you have in the homology of the you have such a relation, and I'm out of time, so I should stop there.
Correction term, like when your quotient like isn't phono or isn't positive.
Yeah, exactly right. So in that case, the QK will be a star homomorphism from if you want to use the small quantum product upstairs, this will go to some T beta of the quantum homology downstairs, where this beta incorporates the bubbling. So it will be 0 in the phono cases, and then in the phono cases, exactly these relations will determine the small quantum homology. But otherwise, the relations are giving you the bulk deformed quantum homology, some bulk deformation, which is coming from counting the additional bubbling. Who's asking the question, by the way? Your voice sounds familiar, but I can't see.
I was asking it.
Oh, Matthew, yeah.
Oh, it was Justin. I was asking.
Oh, Justin. Okay.
Hello, can I ask a question, Chris?
Of course, yeah.
Yeah. Okay, so this is a slightly vague question, but this quantum cohomology you defined yesterday using those 3-point invariants, which you call the small quantum cohomology. So can you define have this same discussion of today with the big quantum cohomology, where you involve the multiple point Gromov-Witten invariants? And is there some similar theory like this? What you discuss, like the analog of QK for that kind of a object, or does it not make sense?
So in general, yeah, thank you. So in general, there's some sort of, let me call it QK twiddle, which is a nonlinear map from the quantum homology equivariantly of M to the quantum homology of the reduced space. So it's a general feature that, you know, a lot of these structures for quantum cohomology is some sort of obtained by taking some derivatives of some nonlinear thing, like the quantum product, for example, or the third derivatives of some potential, Gromov-Witten potential. So here again, there's some nonlinear map, which goes this direction. So if I have a beta, then it goes to some qk of beta, and take qk at beta to be the linearization of qk twiddle at beta. So then this goes from t beta qhg of m to t of qk twiddle beta of qh of m red. And this is a star homomorphism. So suddenly unable to draw a star. This is a star homomorphism. For any beta. So now it incorporates the big quantum homology. You just have to keep in mind that each tangent space is sent to some potentially different tangent space for the symplectic closure.
Okay, so just a follow-up question to that. I mean, so my motivation for asking this is, so suppose your MRED is, let's say, CP2. So
Yeah.
quantum cohomology of CP2 is well understood. You have Kontsevich recursion formula. So it's a vague question. Can I somehow get insight into that the curve counting question of CP2 through this theory? Like, can I interpret this number 12? Let's say there are 12 cubics, rational cubics through 8 points. Somehow can I interpret it through this language or through this discussion, and by transferring it to the other side?
Well, so then you're really thinking of this QHC3, right? Which is just really ordinary C3. I haven't thought about that particular question, but you're really asking about which invariant is that? Is it a 4-point invariant or?
So that would be an 8-point invariant. It passes through 8.
Invariant.
Yeah, right.
Yeah, an 8-point invariant. So one of the difficulties is that now you want to go outside. You want to take a beta that's not zero.
Yeah. Right.
And now really see where that goes.
Right.
The formulas for the QK twiddle are pretty complicated. So they're equivalent to the mirror formulas that are in given.
Okay.
So if it's, can you remind me, is it possible to extract that number from Giventhal's description of the mirror map in this case?
So Giventhal's mirror map is for Calabi-Yau's Calabi-Yau threefold. So I'm not sure whether that formalism works here. I mean, the derivation I know is from this Kontsevich's recursion formula. You take the project.
Right.
I mean, you use associativity of QH basically. So.
Right. So.
But maybe it comes from Giventhal's thing also. I'm not sure.
Yeah, I haven't tried to do that, so I'm not
Okay.
completely.
Okay.
But let me just emphasize maybe that this is really more useful for getting things like presentation than actually for computing specific Gromov-Witten invariants.
Okay.
So
sure.
What in general is going to happen is that here you're going to have some very simple generators. When you map to here, the generators are going to become more complicated. They're going to become divisors plus some quantum corrections.
Okay.
Even for CP2 when you turn on the bulk deformation. And so it will, go ahead.
Yeah, and no, so what I was saying, maybe CP2 was the wrong example to ask. Maybe let's take the quintic threefold. There, whatever Giventhal's formalism is, there works perfectly. So is that a better question to study through this discussion? I mean, can you extract Gromov-Witten invariants of quintic threefold from this? Even some low degrees, like 287 lines on the quintic threefold or something like that. That would come exactly from Giventhal's.
Yeah, I don't think this is really helpful for computing specific Gromov-Witten invariants.
Okay, I see.
It's really more for seeing the presentations of the
I see.
the rings. Yeah.
Okay.
I mean, another example would be quantum K theory. So,
Okay.
suppose you want to give a presentation for the quantum K theory of CP2.
Hmm.
That then this would help.
Okay.
But if you have some, eight-point invariant that you want to compute, it's probably not any easier than
I see.
those other formats.
Okay. So in that case, we conclude. Let's thank Chris again.
Thank you. And I hope to be there next time. Sorry that I was not here in person.
Sorry?
I apologize for not being there in person.
Oh, but thanks a lot for the really nice lecture series.
Okay, thank you.